let's begin with this first question from the section B, I think. The OMK 2021, which is the Malaysian National Mathematical Olympiad or Olympiad Mathematik Bangsa. Question 1, let me read the question, please. So find all positive integers k and n satisfying the following equation. So the equation looks a bit complex, with k one digits repeated k times, followed by a 0 for 2k plus 3 times, plus a number with a k plus 1 sevens, followed by k plus 1 zeros, plus a number with k plus 2 ones equals to 3n cubed. So how do we find such an equation? Yeah? So also solutions in positive integers. Okay, let's change the screen to the workings which I've done previously. I'll just comment on it, how I get each part. Please take note. So we begin by noting, by adding. Okay, so I realized that I tried a few strategies and the modular arithmetic seemed to be perfect. Something I think, if I'm not mistaken, n congruent of more 10, 3, yeah, or 10 works and all that. So the usual seeking out of contradictions, we hope that, then it doesn't work and all that doesn't seem to happen. That means the equation can happen. Okay, so then after some struggle with it, then I kind of thought of why not? See, the numbers are given on the left. Whenever they give these digits, it's good to get the form of the number. So probably something to do with the form of the number would limit the possibilities for k and n. And such turns out to be the case. So just the general idea behind the solution. It's a little bit rare, I think. First time I'm saying such a thing. Oh yeah, if any mistakes here, it's purely minor. I'm not arguing from any solutions given to me, but just a question. So any mistake is purely my own doing. Okay, so I'll just try to do what I can. I think it's like this. So let's add the first two, last two numbers. I mean, just two. So when I add these two numbers, as you can see, the red ones here on the left corner here, this area. So if you add them up, you can see that it becomes this number at the bottom with 7 repeated k digits, and then 8, 1, and then k plus 1, k plus 1 times of 1. Okay, a bit of a tongue twister there. Okay, then what we do is we copy that number towards the right here and add it to the only remaining number, which is the just part, the 1111 string. Yeah, let's start there. So when we do that, we get this yellow number. It's all easy, as you all can see. You'll know to add the digits, right? I mean, just add the k plus 1 digits, match it up nicely, Okay, just break down the 2k plus 3 like earlier as a k plus 1, 1 and k, so that we can match this part. So 2k plus 2, it matches that perfectly. Extract a 1 and k in front for the 2k. What is the word? 2k plus 3 part with the k in front, like this. All this okay, 3k plus 3 in total. I mean, the digits at the bottom row. So when you add them up, you get this orange number. So you can take your time, look at it, pause the video and see. So I won't go in details. It's quite straightforward. Okay, and then let the first two digits of n cubed be AB. So whenever you put a bar here, like you write AB with a bar, it means that talking about the digits and not algebra. I mean, AB without that would signify A times B. So to not get confused, we use this notation. Okay, and then we require something like n cubed multiplied by 3 on the right hand side, talking about this side now. Just now we talked about the left hand side. So n cubed with the AB at the front here multiplied by 3 should get this humongous number. So it's like 3n cubed is written here, just writing it in the more of the normal multiplication form. Okay, so then the trick was, then I realized that when you start doing that, that the front is a string of ones. So it's this one. So I'm going to use the extremal principle. That is, in this case, we're using it to look at the front digit. Normally, you look at the back digit. The back digit didn't seem to point to any contradiction and seemed to be possible. And that is why I started attacking the front digit. Okay, how many ones can it be possible? So I kind of felt that maybe the string of ones here could be limited. Ever since the fact that it's quite obvious, especially if you have done a little bit of Olympiads, you realize that 37 times 3 is 111. That means there's a multiple of 3 that makes exactly 3 ones, a string of ones. So I thought maybe it cannot be beyond that, according to this question. Okay, so now to prove the second part, this is where it brings us to our second image. Let's have a look at that, please. This is S2. Ta-da-dan. Okay, this is the second image. And then what happened to us? So I bring forth from there the string of ones. So I'm trying to analyze the front part and the string of ones that is related to it. So here we have 3a, multiply 3a and plus some carryover could result in the first two digits first. which is 11. So then I look at the analysis on the right. Please look at the analysis in this green thingy here. Let me just circle like that. So when I, what do we say? Undo like that so I can see where I'm talking about. So the highest is 3 times 9. 3 times 9 is the highest for digit 3 multiplied something. So it's 27. And a carryover is almost at most 2, because previously it's also 3 times something like that. You go from the rightmost, you can think of that. So plus 2 is 29. So it's still less than at each step. At any step, actually, in fact, by thinking from the very right corner, we can see that you can at most get 29 only. So that means there's always a carryover of less than 3. That means a carryover of 3 and above cannot happen. So at most a carryover of 2. So that is where the carryover part, now I know it's at most 0, 1, or 2. So I think of it now, looking at the second digit from the left. That means second digit of the number, which is the B part. So 3B plus something, regardless, the carryover now I know is only going to be regardless 0, 1, or 2, must equal to this triangle, the triangle of the other one. Because the B's carryover, that means the tens digit here is the ones digit here. The ones digit is going to put the 1, of course. And then the tens digit is going to be the carryover for the 3A plus carryover equals to 11. That means the front 2 digits, because you cannot get a 1, right? That's why 3 times A cannot be 1. So that's why it has to be 11. That means in the last part of the multiplication. So this kind of argument is called the extremal principle. But a little arithmetic here. It means very numeric. Yeah? Please take note. Okay, and then the must have a very good sense of the numbers around here. So what happened is, then I realized was, then I put the 0, 1, and 2 because there are only 3 possibilities. So regardless, I can just use the triangle straight away and just put 0, 1, 2. And I realized that, I don't even need to look at the B at this point. So 0, 1, and 2, I add them up. I see that A is not an integer for the first two. Which 3A plus 0 is 11 solves to A is 11 over 3. Second one, 3A plus 1 equals 11 solves to A equals to 10 over 3. And the third one is the only possibility. 3A plus 2 is 11. So which solves to A equals to 3. So that means I knew already the first digit of this number of the n cube must be 3. So now the number takes the form at the top here, which is written as 3 times 3b something blah, 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 and then starts off with a string of ones at the beginning. So to have a carryover of 2 being supplied, why is it supplied? Because we fixed this part. Remember the 3a plus 2, 11. Huh? So you need to have a carryover of 2 from the b given to the a. Think of it like that. Lah. Okay. Easier to think like that. So that means what needs to happen. So 3b plus o, this line here, we copy it down and take a closer look at it here. Please take note. So 3a plus b needs to be at least 20. So this itself tells me that b must be at least 6, because if you have a 5 there, 3 times 5, 15, and carryover is only 0, 1, or 2. We established that with the extremal principle earlier on this green highlighted circle. So that means, this part tells me that. So we combine the 0, 1, or 2. So maximum is 2. 15 times 2 is 17. There's no, we want a number that's above at least 20. So that to get a carryover of 2. That means B must be at least 6. 6 times 3 can. 18 plus 2 is 20. Okay, then we just check manually. So since B is bigger or equal to 6, it's easier to think with numbers at this point, numerically. So I changed this part to 36, 37, 38 or 39 being the B, and second digit from the left to be either 6, 7, 8 or 9. Being digits, they only can be single digit. Huh? Please take note. So we multiply like that to see this part now. So now what can we say? So then I look at the partial product, I call it due to lack of a better word, from second last digits. So 3 times 6. So think like 3 here multiplied with 6 like that, for example. So what happens? 3 times 6 is going to have a carryover of 0, 1, or 2. We established that. So I just copy down the line. Simple only. Just copy the whole thing, 3 times 6, 7, 8, or 9, plus the carryover like that. And then do manual computation to see congruent mode 10. Why am I looking at mode 10? Because I'm thinking of the last digit. Okay, the last digit when you do, that means the numbers, they say we need a 1. Do you notice that the string of ones means the result need to be a 1? That means when the remainder of 10 is the last digit. Okay, so when you check that, 3 times 6, for example, 18 plus 0 is 8. That means 18 1. So you get 8, you put the carryover. 1 is a carryover for the 18. and then you only write the 8. That's what I mean by the modulo 10 here. That means 3 times 6 is 18. You plus with the 1 here, you get a 19. So you write the 9, you bring the 1 as a carryover. So I'm not bothered about the 1. Just want to see the last digit first to be 3 times 6, 18. 18 plus 2 is 20. So you write the 0, and then that's what we're writing here as the brown numbers here. Modulo 10. We call it modulo 10. Remainder when divided by 10. Same thing. So just a simplified way of writing. So 8, 9, 10 is not what we look for. We're looking for, because we're looking at a string of K1s. Please remember that. A string of what? K1s. So a string of K1s there. So I need a 1 there. So none of this is 1 except only when you do the others, only this. So I'm just going to talk about that one. 3 times 7 is 21. Plus a carryover of 0 can cause that. You get a 1. Aha. So 21, you put a 1, you carry over 2. Kind of matches this part also, which is the required carryover of 2. So that means the second digit from the left, or the value of B, is 37. So we know already now the number n cube has its front digits as 37. Aha. So that's how we establish, or what we established from this argument image. Okay, being that said, let's go for the last image and conclude this. Let's change the screen, please, and have a closer look at that. Okay, now we arrive at the third image, which is the only possibility. Now n cube has to form the first 2 digits of n cube is 37. So we know already leftmost digit, 37 times 3. So 37 times 3 is 111. So that means 3 is kind of linked to this. And sometimes in some of the contest problems also. So we try to write about the digit beside that. So we explain the extremal argument. So I suspected that it might not just work. And true enough, this is where the argument gets interesting. It turned out to be quite straightforward, actually. 3 times the box, you realize that 3 times box need to get, because 37 times 3 already create the 3 ones in the front. Think of it like that, the carryover of 2. So that means, like all these are set like this now, based on thing. So 3 times something, the 3 times this box need to get a number ending in 1 for the string of ones, if there is such a number. So is there such a number with a triangle part? That means, could there be a string of 4 ones or more? The answer is no, because 3 times something plus the carryover that's written in this part. Please take note, talking about this section, sorry. Scribble that. So 3 times the box, you must get the carryover, and then you must get this 1. Why is it 1? Why not like 21 or 31, all those kind of things? Because there can be no carryover towards the other side, because 37 times 3 already take the 111. So there cannot be any carryover to add it on, because then none of these digits, or one or more of these digits, will no longer be 1. There might be some other number. Oh, that is why it might equal to 1. But 3 times something plus something, can it be 1? It's a contradiction, which is impossible. With no carryover and this thing, so 3 times something is at least 3. So this is impossible. So you never get this digit onward. So this proves a remarkable fact at this point, which is that the string of digit of k at the start of the number must be less or equal to 3. So we took a maximum ride on it to put it 111, but you must understand that it could have been lesser than 111 if the digits did not exist that far. So this is how the argument is important to complete that, or complement the earlier research like working. So k is less or equal to 3. This is easy because we just put the k is 1, 2, and 3 separately, and you get some numeric numbers. So these are the numeric numbers as shown. You can check it up. Like use the original question, put k zeros means, like for example, I'll just go through maybe the third one. What does it mean when they say k is 3? So k is 3 means like a string of 111k here at the start. So it has k3, k ones, 3 ones, k is 3. This one is 2k plus 3 means the digits of 0, 2 times 3 plus 3. So 6 plus 3, 9 zeros. So I got 9 zeros here, followed by k plus 1, 3 plus 1, 4 sevens. And then k plus 1 0, so 4 zeros. And then next number, k plus 2, 3 plus 2, 5 ones. This is equal to 3n cube. This is a literal number. So we don't need to struggle with it. We can just add it up. So when you add it up, it becomes this huge number divided by 3. Doesn't look like a cube, but actually by looking at the earlier pattern, you can guess, just do a manual calculation to decide that. It's 3333 cube. So the kn, there's another answer here. K is 3, n is 3333. So there are 3 solutions in blue, according to whether this 3, 1, 2, 3. So the answer is there are 3 solutions. Done. So find all positive integers. We just need to list the kn 133, 2333, or 33333 for the values of k and n respectively. Thank you.